So in this video I'm going to talk about the question in thermal and statistical mechanics which appeared in GATE 2015 examination. So let's continue with first question. The statement is, in Bose-Einstein condensate the particles, so we have to make the choose the correct option out of the given option. Okay, so let's first try to understand that under what condition the what's the condition between interparticle separation and the de Broglie wavelength. So accordingly we have to make a decision here. Okay, so when the de Broglie wavelength, which is denoted by lambda dB, when it is much smaller than the interparticle separation, so L, that's the interparticle separation, and lambda d, that is the de Broglie wavelength, lambda dB, that's the de Broglie wavelength. Okay, so when de Broglie wavelength is much smaller than the interparticle separation, then the classical statistics apply. Classical statistic apply. Okay, so whereas in the other case, when lambda dB, that's a lambda dB, it's approximately close to the interparticle separation, or it's larger than the interparticle separation. So that means then the Bay function of the corresponding particle, they can overlap. So then Bay function of particles may overlap, and this gives rise to in the phenomena such as Bose-Einstein condensation. Okay, so therefore C is the correct option here. And let me make another mark here. So the validity of the quantum statistics, that's also judged from this condition, whether lambda dB it's smaller than L, or it's close to L, or it's greater than L. So in the second two cases, these are the region where the quantum effects, they come into picture. So that means the quantum picture will become important when lambda dB it's comparable to the interparticle separation, or it's larger than interparticle separation. So this is used as one of the criteria for deciding the validity of the classical statistics or the quantum statistic. Let's continue with the next problem. The statement is, consider a system of n non-interacting spin half particle. So we are having a system of n non-interacting spin half particle. Okay, each having a magnetic moment mu. So the magnetic moment associated with each spin half particle is mu, and it's placed in a magnetic field V, which is directed along z direction. B, it's directed along z direction. Okay, so let's say it's something, the situation is something like this. Okay, so B z. Okay, if E is the total energy of the system, the number of accessible microstates omega is given by. Okay, so we are given that the interaction E is equal to total energy of the system now. The spin is having two options to either to align along the field direction or in a direction opposite to the field direction. Okay, so accordingly we will define the two different energies. Okay, so here we will assume that E, that is equal to mu B, that's the interaction energy. So depending upon the whether the spin is aligned along the field or opposite to the field, so accordingly a positive or negative sign will be introduced here. So spin can align either along field or opposite to field. Okay, So let's say when it's aligned along field direction, the corresponding interaction energy E, that is equal to minus mu dot B. So when spin is aligned along the field direction, so it is negative basically, okay. And when it's aligned, this is along field, okay. And when it's aligned along the in a direction opposite to the field, so it's minus mu dot V. So that is equal to minus mu V cos 180, okay. So that is equal to plus mu B, okay. Now further we assume that let's say the spins, because we have taken the field direction along the z direction, okay. So we assume that spins pointing along the field, spins pointing along field, so that is parallel to B, so they are equal to n plus, okay. Therefore spins pointing opposite to the field, opposite to Bz, we assume, let's say that number is n minus, okay, such that n plus n minus, that is equal to total n, okay. So let's call this as equation 3. Now the total interaction energy of the spins, that is equal to E, that's given by the number of spins which are aligned along the field direction, that's n plus multiply by the corresponding interaction energy, so that is minus mu V, n plus multiply by minus mu V, okay. And then plus the number of spins which are aligned in a direction opposite to the field, they are n minus spin, and the corresponding interaction energy, that is mu V, okay. So that means because we have called this to be E1 and E2, okay, and we have defined E is equal to mu V. So that means in terms of small e, I can rewrite this as minus E n plus E n minus, where I have made use of the fact that E, that is equal to mu V, okay. Now okay, so that means this is equal to minus E into n plus E in n minus, that is equal to what? So n minus, that is n minus n plus, okay. So that is equal to n minus n plus, okay. So after solving, we will end up with E n minus 2 E n plus, that is the total energy. This is equal to this expression. So let me call this as equation 3. So from here we can immediately determine the value of n plus, okay. So that means if we solve this equation, so n plus will be n plus, you can take it to the other side. So n plus from equation 3, n plus is equal to ne. So from here we can okay, so 2e n plus, that is equal to ne minus e. So that means n plus is equal to n by 2 minus e upon minus e upon 2e, okay. So that is equal to 1 by 2 into n minus e upon e, small e, okay, which is mu v. Similarly, I can prove that n minus is equal to 1 by 2 into n plus e upon mu v. So these are the important results. So now we can immediately write the expression for the total number of microstates that are accessible, okay. So please note that because we have determined n plus here, so n minus we can determine from equation 3 by simply substituting a value of n plus here and then determine the corresponding value of n minus. So that will give us this value, okay. Now the total number of microstates which are accessible to a system, that is equal to the total arrangements of the n spins, that's n factorial, divided by the arrangement of the spins which are pointing in the opposite direction, opposite to the field, that's n plus factorial, and then the spins the remaining spin which are pointing in the other direction, so that n minus factorial. So that is equal to n factorial and then the value of the n plus and n minus, so that is 1 by 2 n minus e upon mu b and its factorial multiply by 1 by 2 n plus e upon mu b its factorial. Okay, so therefore we conclude that option A is the correct one here. So let's take a look at the next problem. The statement is, for a black body radiation in a cavity, photons are created and annihilated freely as a result of emission and absorption by the wall of the cavity. This is because, so we have to pick the correct statement out of these given four statements. In principle, this is because of the reason that the chemical potential of the photon is 0. So here A is the correct option, but let's try to understand why A is the correct option here. Now when we talk about a system with fixed temperature and volume, so for the system with fixed T and B, okay, so as is the case of the cavity here, okay, for which the volume is also fixed and temperature, if it is fixed, okay, then in this particular case the Helmholtz free energy which is written as A, it will acquire a minimum possible value. A will acquire a possible minimum value. So that means at equilibrium when T and V are fixed, okay, so in a system of photon, we say that n is not constrained, but it can take whatever value is going to minimize the value of A, okay. So the n, that's the number of photons, n number of photons is not conserved, okay, because of the process of absorption and emission by the walls of the cavity. So it's not conserved. If let's say if somehow the number of photon that they change by an amount dn, okay, so if that so that is infinite, this is an infinitesimal change in the value of n, infinitesimal change in the value of n, so that is by an, it's changing by an amount dn. So then the f, it will not change, f will not change. The point is that f will try to stay at its minimum value, so that means it will stay at possible minimum value. If it's not changing, so that means df, that's bound to be 0. So that means df by dn, because n is changing by a certain amount, but the Helmholtz free energy, it's responding in such a way that so that it's always at acquiring a possible minimum value, so that df by dn, that's bound to be equal to 0. But we know that the chemical potential is connected to the Helmholtz free energy by this relationship mu, that's equal to df by dn. If df by dn, that's equal to 0, so that implies mu, that's the chemical potential, that's also equal to 0. So that's why we say that the chemical potential of the photon, it's 0 because the photon number, it's not conserved. So that's another way of putting the same statement. So mu is equal to 0. This also implies that the photon number is not conserved. That's another way of saying the same thing. Okay, so therefore A is the correct option here. So let's take a look at the next problem. The question is, the average energy U of a one-dimensional quantum oscillator of frequency omega and in contact with the heat bath at temperature T is given by. Okay, so we can evaluate the average energy by knowing the partition function of a quantum harmonic oscillator. The energy eigenvalue of the quantum harmonic oscillator, they are given by En, that is equal to n plus half h cut omega, where n can take a value from 0, 1, 2 and so on. Okay, so the partition function is given by Z, that is equal to summation over n exponential minus beta En. Okay, and that is equal to summation over n exponential minus beta into n plus half h cut omega, where n can take a value from 0, 1, 2, 3 and so on. And here we can take the common factor outside, so which is exponential minus beta h cut omega by 2 exponential minus beta h cut omega by 2 summation exponential minus n beta h cut omega, and n ranging from 0 to infinity. Okay, so that means this is equal to exponential minus beta h cut omega by 2 into, so when n is equal to 0, so that means 1 plus exponential minus beta h cut omega plus exponential minus 2 beta h cut omega plus so on. So here that is equal to exponential minus beta h cut omega as it is, and now the sum of this series. Okay, so that is a plus ar plus ar square, so that is equal to a upon 1 minus r. Okay, so that is equal to 1 minus exponential minus beta h cut omega, and this can be further rewritten as 1 upon exponential, so this is 1 by 2. Okay, so 1 upon exponential beta h cut omega by 2 and then minus exponential minus beta h cut omega by 2, so that is equal to 1 upon 2 1 divided by 2 sine hyperbolic beta h cut omega by 2. That's the partition function. Okay, now once the partition function is known to us, then we can immediately determine the average energy of the system U by making use of the relationship U, that is equal to minus curly beta of ln z. Okay, so that means that is equal to minus curly beta of ln z ln 2 sine hyperbolic beta h cut omega by 2 and its power minus 1, because it's in the denominator, so minus and minus that will become plus, so ultimately that is equal to curly beta of ln 2 sine hyperbolic beta h cut omega by 2. Okay, so we have to find the differential of this quantity, so that is equal to, so average energy U, that is equal to 1 upon 2 sine hyperbolic beta h cut omega by 2, and then again the differential of this quantity, that is 2 cos into 2 cos hyperbolic beta h cut omega by 2, and then differential of beta h cut omega by 2 with respect to beta, so multiply by h cut omega by 2. So that means our final answer is, so it is 2 will cancel with 2, so U is equal to h cut omega by 2 multiply by cotangent hyperbolic beta h cut omega by 2. Okay, so that's the average energy. So that is h cut omega by 2 multiply cotangent beta h cut omega cotangent hyperbolic beta h cut omega by 2. Yes, so that is option A is the correct one here. Let's take a look at the next problem. The statement is the entropy of a gas containing n particles enclosed in volume V is given by this expression. Okay, so S, we are given the entropy in terms of base thermodynamic parameter of the system N kV ln AV e power 3 by 2 divided by n power 5 by 2. Okay, that's the entropy of the system. Okay, where E is the total energy of the system, A is a constant, and kV is the Boltzmann constant. The chemical potential mu of the system at temperature T is given by. Now here we are going to make use of the result that we obtained from the thermodynamic potential du. So let me quickly take you through that result, and then we will immediately find the expression for the chemical potential from the given value of S. Okay, so the thermodynamic potential that we require, that's the internal energy change du. Because here it's the energy E that's given to us, so instead of U I will use E, dE. Okay, so this is dE, and then okay, let me just call dE, that is equal to TdS minus PdV plus mu dN, when we are also taking into account the chemical potential. So that's the equation 2. So from here I can define T, that is equal to dE by ds, okay, by keeping n and v constant. Okay, or from here I can define 1 by T, that is equal to ds by dE. Okay, and also I can also define from here, from the equation 2, mu, that is equal to dE by dN, mu that is equal to dE by dN if I am keeping S and V constant. So then these ds and dV, they will disappear, that become 0. Okay, so now with the help of these two parameters I can define a relationship between the chemical potential and the entropy of the system. So that's what we require here for evaluating the chemical potential from the given information about the entropy. Okay, so in principle, if this relationship it's already known to you, then you need not to go through this entire this procedure, so we can skip this step here. Okay, so I'm going to multiply 1 by T with mu, and that is equal to ds by dE, and then mu is equal to dE by dN SB, and here it is NV. Okay, so by making use of the reciprocity theorem, this is equal to minus ds by dN. Okay, so and by keeping the other natural variable constant V and E constant. Okay, so that's the result. So from here we notice that mu, that is equal to minus T ds by dN by keeping E and V constant. So let's call this relationship as equation 3. So now we will make use of this result, and then we will evaluate the expression for the mu. So let me go to the next page, because it's not possible to write all things here. Okay, so that means, okay, so the expression for the S is, that is equal to n kV. This is the given expression. S is equal to n kV ln AV e power 3 by 2 divided by n power 5 by 2. Okay, so mu, that is equal to mu is equal to minus T ds by dn. So that will be simply require the differential of entropy with respect to n by keeping all other parameter constants, that is by keeping E and V constants. So that is equal to minus T outside and then curly n of n kV ln AB e power 3 by 2 upon n power 5 by 2. Okay, so we have to evaluate this differential and that will give us the final answer. So that is equal to minus T as it is, and then inside the bracket, so differential of this, the first term, I'm taking this as first and the other term as the second one. So differential of n kb with respect to n, so that will yield kb multiply by the second term as it is, ln ab e power 3 by 2 divided by n power 5 by 2. Okay, that's the first term. Now the first term as it is, that's n kb as it is. Now differential of logarithmic term with respect to n, so this will give us 1 by x, log of x, that is equal to 1 by x multiply by n power 5 by 2 in the numerator and a b e power 3 by 2 in the denominator. Then differential of the term which is inside the bracket with respect to n, so I will write the constant term as it is, a b e power 3 by 2 and then multiply by differential of 1 by n power 5 by 2 with respect to n. So here in the numerator it will become n power minus 5 by 2, n power minus 5 by 2. So we have to differentiate it with respect to n. So we will have minus 5 by 2 and then n power minus 5 by 2 minus 1. So it will become ultimately 1 upon n power 5 by 2 and then multiply by 1 by n. So that's the so that will give us the result. So let's see which terms can cancel with each other. So this will cancel with n power 5 by 2 and what else is left? Yes, n will also cancel with this n here. Okay, so that means we are left with, so I will take this kb outside here and this kb also outside here because it's common here. So that is equal to minus kbt and inside the bracket I am left with ln abe power 3 by 2 upon n power 5 by 2. That's the first term. Okay, and then we are left with only minus 5 by 2. Okay, so mu is equal to this expression. Okay, remember that if this expression is directly known to us, then we can skip the previous step for determining this expression. Okay, so then we can quickly differentiate entropy as a function, entropy with respect to n, then we can arrive at this final result. So let's see which one is the correct option. So from here we notice that A is the correct option.